Welcome to this video on electric flux part 2 and an introduction to Gauss's law. Now, this is a super important part of understanding electromagnetism. Gauss's law is a mathematical concept that can be used in multiple applications and theoretically, but in electromagnetism, it lays the foundations of what we know as Maxwell's equations, which are the four fundamental equations of electromagnetism, something akin to Newton's laws of motion. So it's very important to understand this because it's going to be used multiple times. Now I have a few images drawn on the page here, and we're going to start with these two over here on the right because we were looking at this concept of flux in the last video, and the concept of flux, remember, was here specifically electric flux, was defined as the amount of electric field that's passing through the surface of a specific area. And we remember that this should be EA cosine theta because it's a dot product. Now in this video, I'm not going to vary the angle very much here. I'm going to keep it the same, but I'm going to talk about the direction of the angle, okay, or the orientation of the plate relative to the field lines so that we can begin to understand how we might do something like this where we have what we call a closed surface. Here, of course, this is not a closed surface, it's just a little piece of a surface, but here the surface completely encapsulates the charge that's inside. Now, if we look at the field lines that we have here, these ones are pointing from left to right, so we might say that these field lines are pointing in the positive x direction, and these are pointing in the negative x direction. But more importantly, what we want to look at now is the angle of E relative to A. Instead of looking at an absolute direction on our Cartesian plane, we want to use this relative angle between the two vectors. So let's just first think about this. If these are my field lines, I want you to think about where would the more positive region be? Well, hopefully you were able to answer it would be over here because the field lines will point away from the more positive region towards the more negative region. And then over here, of course, the positive region would be here, negative region over here. Now that's going to become important as we slowly build up the concept of what Gauss's law is actually going to be used for in electromagnetism. But for right now, let's just talk about the idea of the angle. So here's my surface area, and you can see that these arrows are passing through the area, and the area vector, right, is normal to the surface. And right now we could say that the angle is equal, so the angle between E and A is equal to 0 degrees because they both point in the same direction. Whereas down here, if the front face is still facing to the right, as we see, but the arrows are pointing in the opposite direction, this angle is equal to 180 degrees. So in this case, because the cosine of 0 degrees is equal to 1, and specifically positive 1, the flux here, the electric flux, is going to be a positive value. Down here, the cosine of 180 degrees is actually going to be equal to negative 1, so the electric flux is actually going to be a negative value. Now this becomes very important when we're going to look at the concept of what we refer to as the net electric flux. Now remember that net anything means that I have to add up components of flux in maybe different directions or the same direction, and I would get a total amount of flux in a given situation. So in the cases right here, like in this case A, maybe we call it up here, there's just a positive amount of flux, and there's really only one area that we're referring to. And down here, same scenario. But if we go over to this closed surface here, we see that the area vector at any given time, so the outside of the sphere is the positive face, so we could say that the area vector points out at all positions. And so we can see that at any given time, it's going to be pointing in the same direction as the electric field lines. Now, instead of writing the individual area, right, I'm going to actually say that a tiny little piece of this sphere is going to be an area differential. Because what I'm going to have to do is I'm going to have to add up all these pieces, because we can see that at any given time they're not pointing in the same direction, that the area is a closed surface that's surrounding the source of the electric field. Now the good thing is that the area at any point is still at 0 degrees to the electric field. Now anywhere on this surface that we might choose, maybe at any point along this surface, the electric field is a constant value. And that's a trick that we're going to use over and over again when we actually try to use what's called Gauss's law. Now let's actually discuss what Gauss's law is specifically saying. What Gauss's law says is that if I enclose a charge in an imaginary surface, the amount of flux that is present, so the amount of electric field that's passing through that imaginary surface, is actually not only proportional to, but equal to the amount of enclosed charge divided by the vacuum permittivity constant, or the permittivity of free space as it's sometimes called. This is a super simple looking but super important equation and relationship that we use in electromagnetism. And it actually makes a lot of sense even on the most basic level, because all it's saying is the amount of field that's passing through this imaginary bubble has to be proportional to the strength of the charge. So if there's a larger charge in here, now I'm not talking about the volume of the charge, but the charge itself, right? So let's say if I had 2 coulombs of charge in here, I'm going to have X amount of flux. If I change this now to 12 coulombs of charge, then I'll have more electric flux, so more field passing through. So it makes a lot of logical sense to what we've been talking about before. But what we're going to see is that this becomes an extremely important term that we'll be able to use over and over again to do lots of different things, including figuring out an equation for the electric field so that we can figure out how the electric field varies as we move from place to place. Now, in figuring out the net amount of flux, right, what I'm going to have to do here is that if the area is something that needs to be added up, right, we've just established the idea that the electric field is constant anywhere on that surface area. So this value right here is going to be constant, and we'll talk about times when that is and isn't constant. And this area is, we're going to change this to a differential form, because what we've got to say is I'm going to just take this tiny little bit of area where that electric field is, and then I'm going to add it to the next little piece, and then the next little piece, and the next little piece, and the next little piece, and so on and so forth until I've summed up the entire area of this sphere, so that I can know the net amount of flux that is present. And so I'm going to write this in 2 different forms. So let's make a little room here. And what I'm going to say is that if I had a way to add up this flux, I could use a Riemann sum form, right, where I would add up that product over and over and over and over again. But what I'm going to show, and what we know to be true over a lot of the physics that we've learned, even when we were looking at how to find the total charge just recently, I'm going to write the differential form of the electric flux equation. I'm going to write d phi is equal to E dot dA. Now what I've done here is I've said if E is constant on this surface that I chose, if I add up all the tiny little pieces of area times the field, which is constant in all of those areas, and then I sum all of those up, so I'm going to go ahead and put my integral sign here, that on this side I will get the total flux, or the net flux, and on this side I would have now an integral definition for calculating the amount of flux. Now keep in mind that all of this is equal to the enclosed charge divided by epsilon naught, the vacuum permittivity constant. And so what I have here is the more useful form of Gauss's law. Now remember, Gauss's law is the thing that specifically says the amount of enclosed charge divided by the vacuum permittivity constant is equal to the amount of electric field passing through the chosen Gaussian surface, as we would call it. And what we're going to do here is we're actually going to draw a little circle over here on the integral sign, and we'll talk about this in subsequent videos. But basically what this is saying is it's a closed surface integral, so I'm adding over a surface that will eventually be closed for that particular function. Now when I actually do the integration here, the e is constant, so we'll talk about how that constructs as we go and how you actually calculate the surface integral. But that's not for this video. This video is just to set up some of the ideas. And I'm going to leave you with a little challenge since we haven't had one in a bit. And I want you to look at this picture over here where I have this purple closed Gaussian surface. I'll go ahead and write that out since I've said it a few times. A Gaussian surface, and remember, a Gaussian surface is an imaginary surface that we use to enclose a charge to determine how much charge is enclosed in order to calculate the flux. Now over here I have these arrows, these electric field vectors pointing in towards the charge, so that means this charge must be a negative charge. And what I want you to do is I want you to determine what the net flux will be. So what will be the net electric flux in this circumstance over here? In other words, would it be positive, negative, and try to give an explanation for how that would come about. Obviously, you're not making any specific calculations, but you're just trying to explain to make sure that you understand the basic concepts of how net flux is determined.